I'm ready. I'm ready. Thank you. So, scalar product. I got you to open up to page 426 because that's where it starts talking about it in the textbook. But what have we got? We've got two ways of expressing the scalar product that are given in the textbook. So we have two vectors, A and B. So we're going to have A vector, which I'm just going to notate with a squiggly underline. That's my preferred way of notating a vector. So A vector. And then we've got B vector, like so. And we're using this dot to represent multiplication. And we're writing it as A1, B1 plus A2, B2, where A1, A2 are the components of the A vector, and B1, B2 are the components of the B vector. And if it were a three-dimensional vector, then it would be plus A3 times B3. Okay, we good with that so far? We also see that the dot product can also be expressed as the magnitude of the A vector times by the magnitude of the B vector times by the cosine of the angle between the vectors. So it's always the angle, the vectors are going away from each other here, and the angle is in there. So those are the two expressions or equations which relate the dot product. What I like about the dot product is that it's one of the first operations that you've come across that's had to be defined personally for a particular context, in this case, vector multiplication. It's a definition. So when we look at these two expressions, this here, which I'm underlining now, is the definition of a dot product. In other words, we have, or not we personally, but mathematicians define this operator called the dot product to work on two vectors, A and B, and the result is a scalar, a number, which is determined by multiplying A1 by B1, A2 by B2, and A3 by B3. And we only deal with 2 and 3 dimensional vectors, but we could deal with 50 dimensional vectors or 1,000 dimensional vectors if we wanted to. University level maths, that's what we do. That's what makes us better than physicists who sort of cop out after about 18 dimensions. Mathematicians are better. But that's our definition. So this line here is definitional. This one here is a derived result. Okay, so anyone who watched video 2 will know why this particular expression works or equation works. It's based off the cosine rule, and it turns out that given this definition, this is also true, that A vector dot multiplied by B vector is equal to that expression there. Okay, so either of these will give us the same value, but it's a definition. And the one thing I wanted to mention is that when we establish a new operator, you need to check your assumptions at the door. You need to actually think about what they mean and actually prove them to be true. Now, I don't need to prove them to be true in the context of this course, but I just wanted to raise your awareness that when you come across a new operator, don't assume things to be true. So, for example, is it true that A vector dot product with B vector, is it true that B vector dot product with A vector as well? Do they give the same value? The answer is yes, they do. But you have to kind of prove that. Well, mathematicians have to prove that. They can't just assume it to be true. Okay, this is called the commutative property. So in other words, we know that commutative property works for multiplication, AB equals BA. We know it works for addition, A plus B equals B plus A. We know it doesn't work for subtraction. That's not true. Well, I've got to put a not equals there. Okay, so we know it's that for operators, and by operators I just mean the symbol here, and multiplication is understood to be in here. We know that it's not always true, and we should never assume it's true. We should either seek confirmation, e.g. look it up, or prove it by thinking about the vectors themselves and seeing and imagining and actually working it out using algebra to determine that it's true. So it is true that this is called the commutative law, and it is true that the scalar product is commutative. And another one, for example, is the distributive law. Is it true? Is this true? You can't assume it's true. It turns out to be true. Okay, so it is true, but you can't assume it's true. So when you come across a new operator, bottom line is don't assume. Even when we come across a new concept like vectors, we couldn't assume stuff about A vector minus B vector. We actually have to work out what subtraction means for vectors and so on. So we really need to think, go back to the start and think things through first. Yeah, so that's all I wanted to say on the scalar product, that they're the two forms, and we're going to use those two forms in order to solve problems. What I'm going to do now is I'm going to go through some examples from... before I do that, I just remembered that I just wanted to quickly touch base from the textbook and the next page along, I think, so page 428. Given that those properties are true, those two vectors are true, so the scalar product results are true, there's a few things that we can determine to be particular properties of the scalar product. So, for example, if A vector and B vector are perpendicular, then the angle between them would be 90 degrees. And because the cosine of 90 degrees is 0, it means that the dot product must be equal to 0. So the idea then, I'm just going to flick back to the notes. The idea being that if you're using the definition here of the vector, of the scalar product, sorry, I'm confusing my words around. If you're using this definition of the scalar product, I'll zoom up on it, and it turns out that the result here is 0, then you know that the vectors are perpendicular. Obviously, if you knew that the angle between the vectors was 90 degrees, you'd know that they were perpendicular just by the definition of perpendicularity. But I'm saying that if you didn't know the angle between them, but you did this calculation and it turned out that the end result was 0, you can also conclude, oh, they must be perpendicular. Does that make sense? So what you're seeing there in the textbook, which I'm going to flick back over to now, what you're seeing there in the textbook is an explanation as to why it is so, but how you actually use it in problems is, if the scalar product is 0, then you can just conclude that they're perpendicular. Parallel vectors, so they're going in the same direction. Then the angle between the vectors is 0, and the result is as follows there. The scalar product will just be the product of the magnitudes. And that third one there is not coincident vectors, but coincident vectors. Does anyone know what coincidence means? Want to have a go, Elizabeth? Yeah. Same endpoints, start and end points. Yeah, they're the same. So they're two vectors that basically lay on top of each other. Same endpoints. They lay on top of each other. So they're basically equal vectors. And it's because they're equal vectors, you have this property, A squared. So basically, if you're given two vectors and it turns out that using the scalar product, one of those results up from the other screen, if it turns out that the result is like A squared, then you can say, oh, they're coincident vectors. But they're basically the same vectors. That's basically what it means. Okay, so I just wanted to point that bit out, that there are those three definitions. You're expected to be aware of that and be able to use it. Now, I feel like we're 15 minutes into the lesson, and I feel like I've got masses of examples I want to go through. So what I'm going to do is I'm just going to break it down into just writing out a few examples at once, giving you just a small chance to practice them for a little while, and then moving on to some more examples. I'm not suggesting that everyone can complete all of the problems in the time we've got, but I'd rather just sort of do demonstration of examples and then giving you a little bit of time. So here we go. Right now, we are going to do some examples from exercise 12I on page 427. I'm just going to do a couple and explain as I'm going along, and then I'll give you a chance to do some yourself. So to start off with, I'm going to do question 1A and question 1D, and then I'm going to do 2B, and then give you a chance to practice. So please stop me as I go along. Question 1A. We've been given what the vectors are. So I might just write them down on my screen here, so I've got them. So we've got A equals 2I plus 4j. So, A vector. I know you won't see it on the screen yet. And B vector is I minus 5j. And C vector is 5I minus 2j. 5I minus 2j. Okay, cool. So I've got those. So what you might want to do is, if it helps you, is to write them out in column notation, if that helps. I'm not going to do that, but for example, you could write A vector as being 2, 4, like so, and keep going on for the other vectors as well. I prefer just to read them from the vector notation there, but you don't have to. So the dot product of A and B is quite simple. We just match things up. So we look at the, we just match up the 2 here from the I vector and the 1 here. It's not, doesn't say 1, but it is 1 from the I vector from the B vector. So that equals 2 times 1 plus, and then we've got 4 times negative 5. So 4 times negative 5. So that gives us 2 plus negative 20. So that's negative 18. And that's all there is to it. Any questions about that? That's all right, isn't it? So you're just matching up the components of the vector. All right, question 2. I'm going to go down to slide 3 for that. Sorry, question 1D, beg your pardon. So 1D has C vector dot product with A vector plus B vector. Now I'm going to do this in 2 different ways so you can see it happening, see that it is consistent. So by using the distributive law, I'm going to say that's equal to C vector dot product with A vector plus C vector dot product with B vector. And that gives us minus 5 times 2 plus minus 2 times 4 plus minus 5 times 1 plus negative 2 times negative 5. That gives me negative 10 minus 8 minus 5 plus 10. And that gives us negative 13. Is that okay? Now, just for laughs, I'm going to do 1D again, and this time I'm going to do it like this. C vector dot product with A vector plus B vector is equal to negative 5, 2, going straight into column notation there, dot product with 2, 4 plus 1, negative 5. So I'm just putting it into column notation, which is negative 5, 2, dot product with. Now I have the addition of 2 vectors here. So we know to add 2 vectors together, we simply add up the corresponding components of the vector. So we've got 2 plus 1, which is 3, and we've got 4 minus 5, which is negative 1. So we've got negative 5. Is it negative 5, negative 2? Did I miss a negative there? Yes, you did. Okay, that's fixed now. So it's negative 5, negative 2, which is the C vector, dot product with 3, negative 1, which is the sum of A vector and B vector, just by adding the components together. Okay, now I'm going to dot product them, and I get negative 5 times 3 plus negative 2 times negative 1. And negative 5 times 3 is negative 15. Negative 2 times negative 1 is positive 2. And that gets me negative 13, which is the same as what we got in slide 3. Yeah? So either approach would have worked. And it depends on where you feel more comfortable with, really. I need to move on to the next slide for a second. So I'll just give you a moment to write those down. And then the last example I'll do before I give you a chance to do some of your own is question 2b. Does anyone have any questions yet? Okay, I'm going to switch on now, so sorry if it's a bit too fast for some people. So 2b uses different vectors, u vector, v vector and w vector, and they are presented in column format already. So let's just get stuck straight into it. We've got 2b says, what's u vector dot product with v vector minus w vector? Sorry, my vector symbols are a bit dodgy. So u vector dot product with v vector minus w vector. So I'm going to go straight into a little bit of notation here because I know subtracting a vector is the same as adding its negative. So I'm going to go u vector dot product with v vector plus negative w vector. And I know that the negative of a vector is simply multiplying each of the components of the vector by negative 1. So I'm now going to go into my notation, which is for u vector, negative 1, 0, 5. And I'm going to dot product that with 4, negative 3, negative 1. That's v vector plus, and I'm just going to reverse the sign in the w vector. So the w vector was negative 1, 3, negative 6, and now it's 1, negative 3, positive 6. Okay, so that's an example of how I do subtraction of vectors. I just add the negative. And by adding the negative, I'm simply changing the sign of each part of the component. I hope that makes sense, and if it doesn't, let's put a star next to it so I can come back and explain to you. I'm now going to just work out the brackets, really, rather than try and using the distributive law. I think that would be pretty ugly to use. So you've got negative 1, 0, 5 is the u vector, dot product with 4 plus 1 is 5, and then minus 3 plus minus 3 is minus 6, and negative 1 plus 6 is 5. So I've got the dot product of those two vectors, which I'm then going to write down as negative 1 times 5 plus 0 times negative 6 plus 5 times 5, and that's going to equal negative 5 plus 0 is negative 5 plus 25 is equal to 20. And we're done. What do you think? Is that okay so far? All right, so I'm going to give you 10 minutes only. In question 3, it asks you to consider whether the vectors that are given are parallel, perpendicular, or neither. So I'm just going to do 3A and 3F. I'm not covering all possible situations, but I thought if I just give you a couple of examples, it's enough to at least give you an idea. So 3A, A vector is equal to 2I vector plus 4J vector. B vector is equal to 4I vector minus 2J vector. And the dot product of those two vectors is we just match up the coefficients, don't we? So the coefficients of I vector are 2 and 4, so it's 2 times 4. And the coefficients of the j vector are 4 times negative 2. And we can see, I think, that 2 4s are 8, 4 times negative 2 is negative 8, and so the result is 0, and therefore we can conclude perpendicular. And 3f, do I have space to do it there? No, I'll just do it on the next one. 3f, n vector is equal to 2y vector minus 8j vector. M vector is equal to negative I vector plus 4j vector. The dot product is equal to 2 times negative 1, so negative 2, and negative 8 times 4 is negative 32, so that's negative 34, and so therefore it's neither 0, it's nothing particular, so it's neither. So there you go, that's basically what you do. You're using the dot product to work out a single number, and then you're matching it against what's required for perpendicular or parallel, and therefore coming up with a conclusion. So I'm going to just give you, just a bit under 10 minutes, about 8 minutes to do that, and then we'll finish off by looking at questions 6, 7, and 12, maybe just question 6. So question 6 is the first time really we're asked to use the alternative version of the formula in order to work it out, because you are asked to find out the angle between the vectors. So we're going to use this notation here, that A vector dot product with B vector is equal to the modulus of A times A vector, the magnitude of A vector times the magnitude of B vector cosine theta. Now I should tell you that the formula sheet gives that you receive in the exam has this notation in it, but it also has this notation where we make cos theta the subject of the equation. So if I divide both sides by A modulus times B modulus, we will get cos theta on the left-hand side here. We'll get the dot product here, and we'll divide it by the magnitude of A vector times the magnitude of B vector. So we're just rearranging our equation with cos theta on the left there. That's all that is. Now you are told that the dot product of A and B vectors is root 6. So I can just substitute that straight in like that. You're told that the modulus of, I keep calling it modulus because it's the same symbol, that the magnitude of A vector is root 3, and that the magnitude of B vector is 2. So we have root 3 times 2. Do note that's not root 3 times 2, that's root 3 times 2. Now, looking at this bit here, the root 6 over the root 3, I can simplify that because they're both square roots, I just divide those two numbers together there. So that means I've got 6 divided by 3, which is 2. So I've got root 2 on 2. That's what cos theta equals. Now, I am not going to reach for my calculator because you should be able to identify immediately what angle gives us root 2 on 2 when put into the cosine function. Can anyone tell me immediately? Yay, 45 degrees, well done, Ollie. So that's 45 degrees or pi on 4. That's question 6 done. Again, feel free to go back and do some of your own practice for the next 7 or 8 minutes until it's changeover time. But for the purpose of this video, and for those that would prefer just to see more examples done, I'm now going to move on to question 7. That was question 6 I just did. Now I'm going to do question 7. Okay, I think I'm just doing 7A by the looks of my notes here. So 7A. We have A vector equaling 2, negative 1, and we have B vector equaling 2, 5. So the first thing I'm going to do is just work out the dot product of that. So A vector dot B vector is equal to 2 times 2 plus negative 1 times 5. So that's 4 minus 5, so that's negative 1. Okay, that's good so far. Then I'm going to work out the magnitude of each vector. So the magnitude of a vector is equal to the square root of 2 squared plus 1 squared, plus negative 1 squared, which is equal to the square root of 5, just by calculating that. And the magnitude of b vector is equal to the square root of 2 squared plus 5 squared. 2 squared is 4, 5 squared is 25, so it's the square root of 29. Okay, I try to keep things as exact as possible when I'm solving problems, so I don't reach for my calculator until the very last moment if I can help it. So we've got the alternative form of denoting the dot product, which is modulus of, the magnitude of A times the magnitude of B times the cosine of theta. Now I can substitute in all those values I worked out. So the dot product was negative 1, the magnitude of A was root 5, and the magnitude of B was root 29. And then I've got my cos theta, which I don't know. Now root 5 times root 29 is root 145. Just a calculator operation if you can't do it in your head. And I've got cos theta there. And now I'm going to divide both sides by root 145 to work out what cos theta is. I've seen problems, by the way, that ask you to find the cosine of an angle. So if the question said, what is the cosine of the angle of these two vectors, then you would stop right there. Okay, that is the cosine of the angle. But if you're asked to find out the angle, then you have to work out the inverse cos, right? So just be mindful of that. I might just do that. So that's where you could stop if that was what it was asking. Otherwise, you would go cos inverse of negative 1 on root 145, and everyone knows what that is. That's one of our common angles. It's 94.8. It's not a common angle at all. So you'd be using your calculator for that to work out 94.8 degrees. Any questions about that? Louis, was that you saying you knew that it was 94.8? So good. What's your memory palace? You got a big memory palace. Okay, I'm going to do question 12 now. Have I got time? Yeah, I got time. So question 12. Question 12, I decided to draw a little bit of a diagram for it. It doesn't matter. Question 12 actually asks for, I'm just going to show it on the screen now. Question 12 says the position vectors A and B. I don't like how it's expressed here really, but position, because that's not in vector notation, but the position vector is 4i plus 4j minus 4k. They're three-dimensional, but don't stress about it too much. It's relative to an origin O. So it kind of, because position vectors are from an origin point here, it kind of means that you've just pick any old direction there and say this is the point 4, 4, negative 4, and then any old sort of direction here. My diagram might be wrong, but I'm just having a go at it. 1, 2, was it 1, 2, 3? I thought I've got my notes, but I feel like that's weird. No, it is 1, 2, 3. 1, 2, 3. It would be the end points, and this would be 0, 0, 0, right, for the origin. So that's basically my diagram, and it says what's the distance between those two endpoints, basically. So we've got this distance here. Now the problem is that we can't add these two vectors together to work out what this one is, because this length and this length is coming from the one spot, whereas addition of vectors has to go top to tail. So there's my tail of my vector, and then I go in a direction, and then my next vector goes in a different direction like that. Then this would be the addition. So if that's A vector and that's B vector, this would be A plus B vector. Okay, that's how it works. So because these are both going in the same direction, then we can't use vector addition in order to work this out. But what we can do is we can basically take a vector which is on top of it, but going in the opposite direction. I'll just draw it next to it. like so. So if we start from here, go back to 0 and then go up to here, then this will give us a vector here that I've put a blue arrow on. It'll be that vector in that direction, but it doesn't matter what direction we've got because we're only interested in the distance. So if we can work out the magnitude of that vector, then we are good to go. So we can use vector sums in order to work out this vector here, and then we can use the magnitude function to work out the length. So given that it's now 11:25, Ashley, I think I might pause there and say I'll return on Thursday to fleshing out this particular example in a different video, and we'll start the lesson with that before moving on to some new material. That's it for today. Thank you.